This is part 2 of Module 12, where I will be giving examples of steady-state AC circuit analysis using the Phasor method. In the previous module, I mentioned that when you transform a circuit into its frequency domain equivalent, you can use all methods of analysis developed for resistive circuits. In other words, you can do network simplification, you can apply or simplify impedances in series, simplify impedances in parallel, and perform Y to delta and delta to Y conversion. You can also use the principle of voltage division and current division. You can do node and mesh analysis. You can apply the principle of superposition. And whenever you have circuits with sources, you can simplify those circuits using Thevenin's and Norton's theorem. Let's take a look at circuit simplification. Let's consider impedances in series. Supposing I have n impedances, Z1, Z2, Z3, all the way to Zn, if these impedances are in series, then they can be combined into a single impedance, Z equivalent. Z equivalent will just be equal to the sum of the individual impedances. So Z equivalent would be Z1 plus Z2 plus all the way to Zn. And this is very easy to prove. We proved this when we considered resistances in series in early part of the course. So I'm not going to go through the proof of this anymore. What about impedances in parallel? If I have n impedances in parallel, that can be replaced by a single impedance Z equivalent, where Z equivalent is equal to the reciprocal of the sum of the reciprocals of the individual impedances. Again, Z equivalent is the reciprocal of the sum of the reciprocals of the individual impedances. Actually, the reciprocal of impedance is admittance. So this is actually Y1, Y2, all the way to Yn. And the Z equivalent is actually the reciprocal of the sum of the admittances. We have a very special case when you have two impedances, then Z equivalent would be product over sum, Z1, Z2 over Z1 plus Z2. Again, we went through the proof of this early part of the course, so I'm not going to prove this anymore. You can, however, try to prove it as an exercise on your own. Another tool we can use for network simplification is your delta to Y and Y to delta transformation. Delta to Y and Y to delta defines equivalence with respect to 3 points. So for example, if this is node A, this is node B, node C, the delta connected network can be transformed into the Y connected network on the right, so that with respect to A, B, and C, the two are equivalent. In other words, if the left network is connected to a circuit and we replace it with the right network, that circuit will not know the difference between the two. They are equivalent. The formula for converting a delta to Y is as follows, and the formula for converting a Y to delta is as follows. Now, we did not really take this up when we took up resistive networks, so I just wanted to introduce it here just to complete the material. Just a word of caution. When simplifying a circuit, make sure you do not eliminate any circuit quantity that you want to determine. Let me give you an example. Supposing I have two impedances in parallel. So this is Z1 and this is Z2. And what I want to do is I want to compute for I1. I want to compute for the current flowing through Z1. What will happen if I simplify the circuit? If I simplify this as follows, what happened to I1? I1 disappears. So I will no longer be able to solve for I1 because it disappears. So that's the caution that I want you to take. Make sure that when you do circuit simplification, you don't eliminate the variable that you want to determine. Let's do an exercise. I'm given the circuit shown. This is shown in time domain. I want to convert it to its frequency domain equivalent. And I want to be able to solve for the equivalent impedance with respect to terminals A and B. So I want to solve for Z's of A and B. And we are given omega, which is equal to 377 radians per second. So the first step in solving this problem is to transform the network to its frequency domain equivalent. So how do you do that? Well, Z's of L is equal to J omega L. So in this case, this is equal to J multiplied by 377. L is 20 millihenries, so this is 20 times 10 to the minus 3. And this is going to give me J 7.54 ohms. Z's of C, on the other hand, is equal to minus J over omega C. So this is minus J over 377 multiplied by 10 millihenries is 10 times 10 to the minus 3. And this is going to give me minus J 0.265 ohms. So I can now draw my transformed network. I have my 25 ohms here. I have my inductance, whose impedance is J 7.54 ohms. I have my resistor, 20 ohms. I have my 55 ohms here. And I have my impedance, this is J 7.54 ohms. Sorry about this. This is a capacitor. Sorry. This is a capacitor, so this is minus J 0.265 ohms. Yeah, sorry. Okay. Let me make the parallel combination between my 55 ohms and my 7.54 ohms be equal to Z's of x. Okay? And let me make the series combination between my minus j 0.265 ohms and 20 ohms equal to Z's of y. So Z's of x is equal to 55 in parallel with Z's of L. So what is this? No? This is product over the sum. You have J 7.54 multiplied by 55 over 55 plus J 7.54. And by just pressing this on your calculator, you are going to get 7.470 at an angle 82.194 degrees. This is ohms. Z's of y, on the other hand, is just 20 plus Z's of c, which is 20 minus j 0.265 ohms. So finally, what is Z's of AB? So this is A, this is A and this is B. Z's of AB would be equal to 25 in parallel with Zx plus Zy, because you'll now notice that Zx and Zy are in series. Okay. I write that out. That's 25 multiplied by 7.470 at an angle 82.194 degrees plus 20 minus j 0.265, okay, all over 25 plus 7.470 at an angle 82.194 degrees plus 20 minus j 0.265. So again, this is something you can directly input into your calculator, and you're going to get Z's of AB is equal to 11.915 at an angle 9.940 degrees. This is ohms, which, if you convert to polar form, would give you 11.736 plus J 2.057 ohms. So this is my final answer. In other words, with respect to terminals A and B, I can replace this entire network with just a single impedance whose value is 11.915 at an angle 9.940 ohms, degrees. Let's do a second example. Okay, this example was given in the previous module. Okay, although we want to try to solve this using a different technique now. So given V's of t equal to 100 cosine 10t volts, determine V's of L of t using voltage division. So what do I want to do first? I want to transform the network to its frequency domain equivalent. So for my source, I have V is equal to 100 over the square root of 2 at an angle 0 degrees. Now my omega is equal to 10. Omega is equal to 10. Z's of R would be simply 8 ohms, and Z's of L would be J omega L, which is J times 10 times 0.6, or J6 ohms. So what is now my transform network? Okay. So this is V, which is equal to 100 over square root of 2 at an angle 0 degrees. And then I have my 8 ohms here. Then I have my J6 ohms here. And this is now V of L. Okay. How do we get V of L using voltage division? Well, use the formula, no? V of L is equal to V multiplied by J6 all over 8 plus J6. No? This is V of L is equal to V. This is ZL over ZR plus ZL. So V of L equal to V J6 times over 8 plus J6. So this is 100 over the square root of 2 at an angle 0 degrees, J6 over 8 plus J6. And again, using your calculator, you're going to get 30 times the square root of 2 at an angle 53.13 degrees volts. Now, since we're being asked for the time domain, we want the time domain expression, we would have to convert this to time domain. So that would be V of L of t. Note we go from uppercase, which you use to denote phasors, to lowercase, which you use to denote time domain expressions. This is now going to be the square root of 2 times 30 times the square root of 2. So we have to convert from RMS value to amplitude. Cosine of omega, which is 10, so 10t plus 53.13 degrees volts, or this is just 60 cosine 10t plus 53.13 degrees volts. So that's my final answer. Let's try another exercise. Okay. So given V of t equal to 200 cosine 10t volts, find I1, I2, and I3. So again, as we've done in all the previous problems, the first step would be to transform the network. So the source, V, would be equal to 200 over the square root of 2 at an angle 0 degrees volts. Okay. Our omega is equal to 10. Okay. For L1, so let's say this is L1, and let's say this is L2. Okay. For L1, JL1 is J omega L1, which is J 10 times 1.2 or J12 ohms. For L2, JL2 is equal to J5 ohms. And then for C, J's of C is equal to minus J over omega C. So this is minus J over 10 times 0.01 or minus J10 ohms. Okay, the resistors are already specified in terms of their impedances. So what is our transformed network going to look like? Okay. So our transformed network will look as follows. No? This is 200 over the square root of 2 at an angle 0 degrees. I have 6. Okay, this is J12. I have 5. This is J5. And I have minus J10. Okay. Now, from this point on, there are several ways of solving this problem. So, let's first try to solve the problem using nodal analysis. Let me do this. Let me define this to be Z1, this to be Z2, and finally this to be Z3. So let me redraw my circuit. I have V, this is Z1, this is Z2, and this is Z3. So I want to use nodal analysis. Okay. In my nodal analysis, I will define this to be node X, and I will define this to be my reference node. Okay. Take note that the voltage at this point will also be equal to V. So applying KCL on node X, okay, I'm going to get Vx minus V all over Z1 plus Vx over Z2 plus Vx over Z3 is equal to 0. Or, okay, Vx 1 over Z1 plus 1 over Z2 plus 1 over Z3 would be equal to V over Z1. This is by manipulating the first equation. So I can solve for Vx. So solving for Vx, I get Vx is equal to V over Z1 multiplied by 1 over Z1 plus 1 over Z2 plus 1 over Z3 raised to the minus 1. No? Because it came from the left side of the equation, we brought it to the right side of the equation, so you have to raise it to minus 1. So now let me plug in my values. I have 200 over the square root of 2 at an angle 0 degrees divided by, what is J1? J1 is 6 plus J12. Okay. Multiplied by 1 over 6 plus J12 plus 1 over, what is J2? J2 is 5 plus J5. And what is J3? J3 is minus J10. Raised to the minus 1. So again, this is just now a matter of plugging this into your calculator. That's why I told you in the last module, in the review of complex numbers, that you to be very adept at performing calculations using your scientific calculator operating in complex calculation mode. Because by just plugging those figures into my calculator, I'm going to get Vx is equal to 50 times the square root of 2 at an angle minus 36.87 degrees volts. Okay, now it's very easy to solve what I1 and I2 and I3 are. Okay. This is I1. This is I2. And this is I3. Okay, what is I1? I1 is just V minus V of x divided by Z1. No? By the way, let's not forget the arrows on top to indicate that those are phasors. So I1 is V minus V of x over Z1. So this is, what is V? V is 200 over the square root of 2 at an angle 0. No? So this is 200 over the square root of 2 at an angle 0 degrees minus V of x, which is 50 times the square root of 2 at an angle minus 36.87 degrees over J1, which is 6 plus J12. And through your calculators, that will come out 7.071 at an angle minus 36.87 degrees amperes. I2 now would just be V of x over Z2. I2 is this voltage divided by this impedance, which, again, just keying that into your calculator, you're going to get 10 at an angle minus 81.87 degrees. Finally, I3 is V of x over Z3, which is going to be 7.071 at an angle 53.13 degrees. This is amperes. Now, since the problem required us to determine the time domain function I1, I2, and I3, we would have to convert these phasors now to time domain. So i's of 1 of t is going to be the square root of 2 multiplied by 7.071 cosine of omega. Omega is equal to 10, so that's 10t minus 36.87 degrees, which is going to be 10 cosine 10t minus 36.87 degrees. This is amperes. I's of 2, following the same procedure, you're going to get 14.14 cosine of 10t minus 81.87 degrees amperes. And i's of 3 would be equal to 10 cosine of 10t plus 53.13 degrees amperes. So these are my final answers. Okay, that is using solution 1, which is to use the nodal analysis. Let's do it another way. Let's use network simplification. So the thing to do is determine the equivalent impedance seen by the voltage source. Okay. So this is my voltage source. This is V. I have Z1, Z2, Z3. Okay. What I want to determine is this impedance. This impedance, Z equivalent, with respect to these 2 points. Okay, it's easy to see that Z equivalent is equal to Z1 plus the parallel combination of Z2 and Z3. Or Z1 plus Z2, Z3 all over Z2 plus Z3. So this is Z2. So this is equal to 6 plus J12, that is Z1, plus 5 plus J5, that's Z2, minus J10 is Z3, all over 5 plus J5 minus J10. And I'm going to get Z equivalent will be equal to 16 plus J12. Okay, when you've computed Z equivalent, it's now very easy to compute for I1. I1 is simply equal to V over Z equivalent. So this is 220 over the square root of 2 at an angle 0, which is the same as 220 over the square root of 2. This is over 16 plus J12. And I'm going to get 7.071 at an angle minus 36.87 degrees, which is exactly what I got here. So they are consistent. How do I get I2? How do I determine I2? If I know I1 and I recognize that Z2 and Z3 are in parallel, then I can just use the current division principle. What is that? I2 is equal to I1 multiplied by Z3 over Z2 plus Z3. This is current division for two impedances that are in parallel. So this is now 7.071 at an angle minus 36.87 degrees multiplied by minus J10 over, what is Z2? Z2 is 5 plus J5, and then Z3 is minus J10. And I'm going to get 10 at an angle minus 81.87 degrees. Okay. How do I get I3? I can also use current division for I3. So I can do the same thing, use current division for I3, or I know I1, I know I2, I can do a KCL in this particular node to determine I3. So using KCL to determine I3, I3 is simply equal to I1 minus I2. This current is this current minus this current. And again, just plugging that into my calculator, I will get 7.071 at an angle 53.13 degrees amperes. Note the consistency between what I got in solution 1 and what I got in solution 2. So this and this. So the time domain expressions will just be the same. So this will be my time domain expressions. Let's do our fourth exercise. This time, let's consider a circuit with two sources, a voltage source and a current source. So here, the voltage source is V sub S equal to 100 cosine 10t, and the current source is I sub S equal to 10 cosine of 10t plus 30 degrees. And the problem is to solve for the current I of X. Again, the first step that we follow is to transform the network. Okay, Z's of L is j omega L, which is j. Omega is 10, L is 0.5, so you get j 10 times 0.5, or just j5 ohms. On the other hand, Z's of C is equal to minus j over omega C. Omega is 10, C is 0.01, omega C is 0.1, so minus j over 0.1 is minus j10. I can now draw my network as follows. I have V's of S, which is equal to 100 over the square root of 2 at an angle of 0 degrees. I have Z's of 1, which is equal to 5 plus j5. Then I have Z's of 2, which is equal to 10, and Z's of 3, which is equal to minus j10. Finally, I'm going to have a current source whose phasor value, I's of S, is equal to 10 over the square root of 2 at an angle of 30 degrees. My unknown is the phasor current I's of X. Again, note that when we go from time domain to frequency domain, the variables become uppercase variables. The first approach that I'm going to apply would be nodal analysis. So let's do nodal analysis on this circuit. Let's say this is node X. Let's call this node X. And let this be my reference or my ground. Applying now KCL to node X, what am I going to get? V's of X minus V's of S over Z1, that's my first term, plus V's of X over Z2 plus V's of X over Z3 is equal to this current source, I's of S. Manipulating, I'm going to get V's of X times 1 over Z1 plus 1 over Z2 plus 1 over Z3 is equal to I's of S plus V's of S over Z1. Solving now for V's of X, I'm going to get V's of X is equal to I's of S plus V's of S over Z1 multiplied by 1 over Z1 plus 1 over Z2 plus 1 over Z3 raised to the minus 1. So I can now plug in my actual values. I's of S is 10 over the square root of 2 at an angle 30 degrees. V's of S is 220 over the square root of 2 at an angle 0 degrees. J1 is 5 plus J5. And then I have 1 over J1 plus 1 over J2 plus 1 over J3 raised to the minus 1. Again, thank God for our calculator, because keying these numbers in, we will automatically get, granted you don't make a mistake in keying in, 68.30 at an angle minus 15 degrees volts. That's the value of V of x. So how now do I compute for I of x? I of x is simply V of x divided by J3. Again, our calculators will show that this is equal to 6.83 at an angle of minus 15 degrees volts. Actually, it's trivial. J's of, no, not J's of 3, J's of 2, sorry. J's of 2. This is J's of 2. J's of 2 is equal to 10. Therefore, 68.30 at minus 15 degrees divided by 10 is 6.83 at minus 15. This is not volts. No? This is amperes. Amperes. So since we are asked to give the time domain expression for I of x, you have I of x of t is now square root of 2 multiplied by 6.83, that is 9.66, cosine of 10t minus 15 degrees amperes. So this is my answer, and I did it using nodal analysis. Let's try a second approach. Let's try superposition. Superposition, I of x would be due to a contribution from source 1 and a contribution from source 2. So the total current flowing through J2 is the contribution from source 1 plus the contribution from source 2. So let's consider the voltage source or source 1 acting alone. So my circuit now is this. This is V of S. I have J1, J2, J3, and to suppress my current source, I replace that with an open circuit. Okay, how do we get, let me call this IX1. This is the contribution to the current IX coming from source 1. Okay, one way of doing this is similar to what we did in the previous problem. I try to get the equivalent impedance of the circuit with respect to the voltage source terminals. So what is Z equivalent? Z equivalent is just Z1 plus Z2 in parallel with Z3. So this is 5 plus J5, that's equal to Z1, plus Z2 is 10, Z3 is minus J10, all over 10 minus J10. And if you key this into your calculator, you're just going to get 10 ohms. So it's now quite easy for me to compute for the value of IS1. IS1 is now going to be equal to V sub S over Z equivalent. So this is 100 over the square root of 2 at an angle 0 degrees all over 10, which is just going to give me 10 over the square root of 2 at an angle 0 degrees amperes. So how do I get now IX1? From current division, IX1 is equal to IS1 multiplied by Z3 over Z2 plus Z3. So this is 10 square root of 2 at an angle 0 degrees multiplied by minus J10 all over 10 minus J10. And I'm going to get 5 at an angle minus 45 degrees amperes. Next, we consider the current source acting alone. If the current source is acting alone, we suppress the voltage source. How do you suppress a voltage source? You replace it by a short circuit. So now my voltage source is a short circuit. I have Z1, Z2, Z3, and my current source. IS. Note that in this circuit, Z1, Z2, and Z3 are all in parallel. So I can actually determine this current, let me call this IX2, the current flowing through Z2 contributed by source 2 or your current source. I can determine this using current division. What is my current division formula? This is now current division for 3 or more elements. Okay, IX2 is equal to IS. The current will divide in proportion to the admittance of the circuit element. So my numerator is going to be the admittance of Z2, so that is Y2. And my denominator is the total admittance, Y1 plus Y2 plus y3. So this is is 1 over z2 over 1 over z1 plus 1 over z2 plus 1 over z3. Okay. So is is, what is is? 10 over the, sorry, let's go back. Is 10 over square root of 2 at an angle 30 degrees. Then you have 1 over z2, which is 1 over 10. Then 1 over, what is z1? 5 plus, is it 5 plus j5? Yeah, 5 plus j5 plus 1 over 10 plus 1 over minus j10. And if you, again, just key that into your calculators, you're going to get 5 times the square root of 2 over 2 at an angle 30 degrees. And this is amperes. Okay. The total contribution of the two sources would give me the value of ix. So that would be ix1 plus ix2. So ix1 is 5 at an angle minus 45 degrees plus ix2, which is 5 square root of 2 over 2 at an angle 30 degrees. And I'm going to get 6.830 at an angle of minus 15 degrees. This is amperes. What did we get in solution 1? Same, identical. Let's do it a third way. Let's use Thevenin's theorem. Okay, when we use Thevenin's theorem, what we're supposed to do is we're supposed to remove Z2. Then we're supposed to get the Thevenin's equivalent of the circuit with respect to the terminals of Z2. So let's do that. So this is V sub S. This is Z1. I removed Z2. So A and B are the terminals of Z2. Then I have Z3. Then I have I sub S. VTH is the open circuit voltage across A and B. Okay. So we have to solve for VTH. To solve for VTH, let's use nodal analysis. Let me assume this is node X, and let's assign this to be our reference. Okay, so applying KCL or applying nodal analysis to node X, I have V sub X minus V sub S over J1 plus V sub X over J3 is equal to I sub S. Or, manipulating that, I have V sub X times 1 over J1 plus 1 over J3 is equal to I sub S plus V sub S over J1. Or, solving for V sub X is equal to I sub S plus V sub S over J1 multiplied by 1 over J1 plus 1 over J3 raised to the minus 1. Again, just feeding in the values for IS, VS, J1, and J3, I'm going to get V sub X is equal to 136.603 at an angle minus 15 degrees volts. Note that V sub X is equal to VTH. The voltage from A to B is also the voltage from the node X with respect to our ground. So V sub X is equal to VTH. Okay. So we have already computed for VTH. Next, we have to compute for ZTH. How do we determine ZTH? That is the impedance looking into A and B with the sources suppressed. To suppress your voltage source, you replace it with a short circuit. To suppress your current source, you replace it with an open circuit. So this is going to be my circuit. So this is my voltage source. I have Z1. This is A. This is B. I have Z3. And then my current source is an open circuit. I can do this because all my sources are independent. When you have dependent sources, then you're going to have a different technique for determining ZTH. So what is ZTH? ZTH is the impedance looking into terminals A and B. And you can see that ZTH is simply equal to Z1 in parallel with Z3. So this is 1 over Z1 plus 1 over Z3 raised to the minus 1. And again, entering Z1 and Z3 using your calculators, you're just going to get ZTH is equal to 10 ohms. So finally, we get the following Thevenin equivalent. This is my V Thevenin, which is equal to 136.603 at an angle of minus 15 degrees. This is my Z Thevenin, whose value is equal to 10. And this is now A and B. In other words, this circuit, okay, is equivalent to this circuit, no? With respect to A and B. The two circuits are equivalent. So for me to determine I of X, what am I supposed to do? I'm supposed to reconnect Z2. So I reconnect Z2. So that will enable me to determine now I of X. Z2 is equal to 10 ohms. So I of X is just equal now to VTH all over ZTH plus Z2. So this is 136.603 at an angle minus 15 degrees over 10 plus 10. And if I carry that computation out, I'm going to get 6.53 at an angle of minus 15 degrees amperes. Again, consistent with solution 2. Oh, sorry, not 53, 6.83, sorry. This is 6.83, 10 angle minus 15 degrees amperes. So consistent with solution 2, consistent with solution 1. What I'd like to point out in this particular exercise is there are really many, many ways of solving a problem. You're only limited in your imagination. In other words, you do what you feel is most comfortable for you, I guess. Okay, so that's the end of Module 12. I hope to have demystified the Phasor method or frequency domain analysis through Module 12.